far away, they're running twice as fast. And when we look out 7.5 billion light years away, they're running away at half the speed of light. And when we look out twice that far away, they're running away at the speed of light. That is the border to the observable universe. And it's 15 billion light years away that way, and that way, every way. And the observer is always at the center. You see, Ptolemy never had this so good. Ptolemy wanted the Earth at the center. This has everybody at the center. That's the fun of it. Now, what do we see when we look out near the border? What we see is that the radiation, you all understand this, the radiation of the things coming, when we look way out at the border, we see the radiation that's coming in is all redshifted. Now, we talked about fire engines, didn't we? Coming toward you, the bell is at a high pitch and going away, ding, 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 goes away at a low pitch. So if the star is coming toward you, the spectral lines are blue shifted, more energetic, and if it's going away, they're red shifted and it's less energetic. So when we look out at the border, we see everything going away, and at 15 billion light years away, they're going away so fast that the energy goes completely to sleep. Okay? Goes completely out. Just a little bit this side of that, we see everything in the radio waves. Okay? That's the picture. We see the energy of the radiation redshifted approaching zero at the border. If the energy of the radiation approaches zero at the border, the energy of the particles giving rise to the energy also goes to zero. Giving rise to the radiation. The energy of the particles giving rise to the radiation also goes to zero. Now, if the energy of the particles goes to zero, the mass goes to zero. If the energy goes to zero, the mass goes to zero.
Wouldn't that be absolute zero?
What?
Wouldn't that be absolute zero?
We don't care about absolute zero. This isn't a temperature problem. This is not a temperature problem. We're just talking about the mass going to zero. Okay? This is not, absolute zero is a temperature problem. This is not a temperature problem. We're talking about the energy of the particles going to zero. That means the mass of the particles goes to zero. If the mass of the particles goes to zero, the momentum goes to zero. The mass times the velocity. This doesn't approach infinity, so the momentum approaches zero. If the momentum approaches zero, our uncertainty in the momentum approaches zero. Is that dreadfully clear to you all? You can't have a big mistake about nothing. If the momentum approaches zero, your mistake in it approaches zero. If our uncertainty in the momentum approaches zero, our uncertainty in where they are goes to infinity. So the particles have to recycle from the border. Sorry about that. No, I'm not sorry about that. But this is true even for the Big Bang model. The particles have to recycle from the border. Now they think there's a big actual universe on the other side of the border. But Heisenberg won't have it. Heisenberg's uncertainty principle requires that the particles recycle in from the border because the mass approaches zero at the border. Now there's another consequence at the border. If the mass approaches zero, all radiation going through a field of low mass particles gets thermalized to 3 degrees Kelvin. Tell you how that happens. If the particles are electrically okay, but very easily shaken, then the radiation always shakes them, and then they re-radiate, and then that radiation gets picked up by more particles, and they re-radiate, and it comes out thermalized at 3K. Now, the amount of background radiation that we get this model is what we actually measure. The amount of background radiation predicted by the Big Bang is about 100 times too much. Now, when the Big Bang people discovered the background radiation, when Penzias and Wilson discovered the background radiation in 1964, the Big Bang people took that to be their own. They took that to be the proof of the Big Bang and the tombstone of the steady state. But it really doesn't work like that. The steady state model gives you the right amount of background radiation, and the Big Bang gives you way too much. Anyway, the two things that the Big Bang people thought were very wrong about the steady state model was that they didn't have any way to get the hydrogen to come back in from the border, but we do have a way to get it back in, and it's unavoidable. And the other was that that the steady state people had no way to get the background radiation. But there we also get the right answer there. Anyway, so these are two of the consequences which we see when we look out at the border. Now, you remember I told you that the rest mass of the particles, the gravitational rest energy of all these particles, is related to their separation from all the rest of the matter in the observable universe. Now suppose the rest of the universe were smaller. Then the particles would be separated from a smaller number of things, and the rest mass would be lower. Is that clear? Suppose we were able, just suppose we were able to make all the particles too heavy. Oh, I haven't told you something. I have to detour. I have to put in another piece. Put in another piece. The question is, what drives the expansion? Okay? The Big Bang people put all the energy into the explosion. They got it from wherever. I don't know where they got the energy, but they put it all in the explosion and let it go like that. See, they have no source for that, all that energy. They just had to throw it in by hand. But the steady state model has a driving mechanism. Because if the universe expands, oh dear, let me go back a little. Why is the night sky dark? Let's go back. Why is the night sky dark? Don't tell me because the sun went around to the other side. That's what the kids tell me. Why is the night sky dark?
Because the earth revolved.
That's what the kids tell me. Sit on
I
it.
said the sun went around.
Sit on it. The problem is like this. This is an old problem. It was done by Chasseau a long time ago, and then I think by Kepler, and then by Olbers, and Olbers got his name attached to it. But at any rate, it goes like this. If the sky were speckled with stars, the way we see it nearby, and if it went forever, the whole night sky would be as bright as the sun. Why? Because if it were speckled with stars, like we see it nearby, and it went forever, wherever you looked, you'd see the face of a star. And since the stars in general are bright, the ones that we see, are brighter than the sun, at least it would be as bright as the sun. The whole night sky would be as bright as the sun. So the question is, why is the night sky dark? So first, those of you who voted that the universe were infinite, was infinite, you can see that it's probably not right. If it was infinite, it should be as bright as the night, as bright as the sun. So why is the night sky dark? First of all, because it has a border out there. 15 billion light years away, there's a border, okay? Beyond that, there's nothing that can shine back at us. Even if there is anything out there, it can't shine back at us. Because so that's the border to the observable universe. And not only that, but partway out, some of the radiation has lost its energy. Okay? Now, if the energy of the radiation gets lost in the expansion, it drives the expansion. Do any of you have trouble with that? If the hot gases in the cylinder of your car don't expand the cylinder and drive the car, you'll boil over. Is that clear? If the hot gases are not allowed to cool off by expanding the cylinder, you'll boil over. So the energy of the hot gases gets lost in the expansion of the cylinder. So the energy of all the radiation in this universe gets lost in the expansion of the universe, and that's why the sky is dark. If the universe did not expand, the energy would not be lost, and the night sky would be as bright as the sun. Is that clear now? Now suppose we were able. It's my turn. If we were able to make all the protons too heavy, then they would fall together too fast. If they fell together too fast, they would radiate too fast. If they radiated too fast, the expansion rate would go up. If the expansion rate goes up, does the universe get bigger or smaller? Come on, come on. It gets smaller. They reach the speed of light now at 15 billion light years away. If you double the expansion rate, they'd reach it at 7.5 billion light years away. Isn't that okay? It doesn't matter if you guess wrong. Just so long as you didn't calculate it. When they come wrong with their calculations, I get upset. If you double the expansion rate, the borders come in halfway, and the size of the universe gets smaller. Now, if the size of the universe gets smaller, the number of protons that these protons have been separated from gets smaller, and their rest mass goes back down. Now, I'll do that again. If we were able to make the protons too heavy, they would fall together too fast, radiate too fast, the expansion rate would go up, the borders would come in, and the rest mass would go back down. Now, this is what I call a steady state model with a governor on it. It doesn't say that it couldn't sometimes be a little bit bigger and sometimes be a little bit smaller. And it doesn't say that one part couldn't be expanding faster than another part. Depends on how much radiation is dumped into the expansion. Any problems with this? Now you see, the interesting thing is that if the universe were infinite, you couldn't budge. Because then all these protons would be separated from an infinite number of other protons, and rest mass would be infinite, and you couldn't wiggle your finger. Finite rest energy, finite mass is available only in a finite universe.
Where's the universe expanding? What's it
What?
expanding into? What vacuum is it expanding?
Who said it's expanding into a vacuum? A vacuum is just something that you invented.
Where is it going?
It's not going anywhere. Just going away and coming back. You see, our guts tell us that there must be a big black empty space out there. There's nothing in the physics that tells you that. It's just a mistaken programming that goes on in our guts. Our guts say that if there's a border, there should be a fence there, and the question is who painted the other side of the fence? That's the big problem. But you see, when you look at it from the standpoint of the physics, it must be that out of the border, the energy runs out to zero, the mass runs out to zero, the space runs out to zero, and the time runs out to zero. Now you see, if this is a dreamlike universe, you don't ask what's on the other side. When you dream, you have a space in which you dream, right? And what's beyond the space when you dream? Oh no, there's the dreamer, you silly. There's not nothing. There's a dreamer. You don't do it in a vacuum. There's a dreamer. Now if this is a boo-boo, there's a boo-booer. But not a big black empty space, like our guts said that there should be. When I was a little kid, I thought, if there wasn't any universe, there'd be this big black empty space in time. I can't think like that anymore. We know perfectly well now that space and time is related to matter and energy are related to space and time. And you cannot have space and time without matter and energy, you cannot have matter and energy without space and time. And there's no such thing as a vacuum. There's no such thing known to man as a vacuum. There are always gravitational fields in it, there are always electrical fields in it, there are always photons in it, there are all this stuff going on. That's just a notion that's presented to us by our genetic programming. We've got the wool pulled over our eyes all the time. As always says, pubic wool.
So this concept of an expanding universe, you're saying that it's always been the same size, that it's just that there's always things expanding to the outside, and then
If it expands faster, it gets smaller. If it expands slower, it gets bigger, yeah.
But when things get to the outside, you said recycle?
They recycle back in? Necessarily, because way out there, if the mass approaches zero, the momentum approaches zero, and the uncertainty of the momentum approaches zero, so the uncertainty of where they are approaches infinity. Now, I went through this at Griffith Park a couple of years ago to the physicist who had just given the lecture in there, and he was shocked. He says, I have never heard the border conditions discussed in this way. He said, of course, they tunnel back in. They tunnel back in. The physicists have a word for this. If an electron goes from one energy level to another in an atom, it does not slide down. It disappears in this energy level, and it reappears in this energy level. These things are not things. Electrons and protons are not things. They're like dollars in the bank. There is no this one and no that one. When you have dollars in your pocket, there's a this one and a that one, but not in the bank. When somebody writes you a check for $3, you don't ask which dollars they were. And the dollars in the bank can do things which dollars in your pocket can't do. If somebody writes a check on a bank in Santa Barbara to a bank in Portland, they disappear in Santa Barbara and reappear in Portland. You must have noticed. These things are like dollars in the bank. There is no this one and there is no that one. Now with pennies, copper pennies, there are four ways to put them down. Heads up, heads up. Tails up, tails up. This one heads and that one heads. The four ways. There are three ways to put down two electrons. Spin up, spin down, and one each. That's all. There's no this one and no that one. Now this kind of thing we can find out from the physics. We can find out for sure whether there are three or four ways to put them down, and there are three. That means there's no this one, no that one. They're like dollars in the bank.
So this relates to, you said, the recycling process they call tunneling when they...
When it goes from this energy level to that energy, it's called tunneling, and it doesn't seem to take any time, and it doesn't seem to matter how long it is, how far away it goes, it doesn't seem to make any difference. But the particles don't come in on the train. They disappear out there, and they reappear in here.
Where do they reappear?
They can reappear any damn place.
Just to keep back.
The uncertainty principle doesn't tell you where. That's why they come back in, because you can't tell where they are. If you know what they're doing, you cannot know where they're doing it. And if you know that they're at the border and not doing a damn thing, they cannot stay there. They can't stay there and do nothing.
But there must be a mass appearing at some place. If
There
energy is
are some people who think that the quasars are new matter coming in. But I don't see any constraint that allows the stuff to come in bunches like that. There may be somewhere some constraint which I have not noticed, because there's some evidence that the quasars really are new matter, and that's why their redshift is so great. If the matter is new, it's had only a little while to be gravitationally aware of the stuff around it. If it's only been here for 8 years, it can know about the stuff almost out to Sirius. If it's been here for 100,000 years, it can be aware of our whole galaxy, but that would still be a very small rest mass compared to being aware of the rest of the universe. So if it's been here for, say, 3 million light years, it can be aware of our whole cluster of galaxies out to the Andromeda Galaxy and beyond. But you see, it would have to be here a long time to be aware of all this stuff. And so gradually the mass would increase as the stuff has been here for a longer time. Now there are quite a few people who are pushing that model. Hoyle and Arf and the Burbages and Narlikar, they have suggested this model, that it might be that the redshift of the quasars is not due to their going away. It's due to the fact that they're new. They don't like the Big Bang model, but if you're going to have bangs anyway, why have just one?
Yes, is that because like the gravitational field takes time to propagate?
That's according to general relativity, but not according to special relativity. According to special relativity, there are no photons and there are no gravitons. There's a space separation and time separation, and the total separation goes to zilch. That's true for gravity and for electricity and magnetism also. But general relativity overlooks special relativity, and then it has this problem. The moon's over here, and the earth is over here, and you can't have action at a distance. And it can't be that the separation is zero. They see the space separation is real and overlook the time separation. So they say that the earth warps the space next to it. And that warps the space next to it. No action at a distance, you see. And it keeps going like this. And 1 1/3 seconds later, it gets over here to where the moon is. And then it notices it. I say it's feces, cattle feces. I don't like general relativity for the simple reason that it overlooks special relativity, and we're quite sure that special relativity can hold its own.
So no one's measured the speed of gravity like that.
No, they can't do that. They're looking for gravity waves. They're not finding gravity waves. But then they haven't found any photons either. Let's face it, nobody ever saw a photon. It's just an invention. All we know about radiation is the emission event and the absorption event. And the equation says they have zero separation in space-time. Nobody ever saw a photon. Light beams are not seen from the side. Are we allowed to leave this thing till tomorrow night?
It's up to you. How long does it take?
What time is it now?
It's just about 9. How long does it take?
Half an hour.
Do you want to
They've run out of ice cream.
ask them whether they want to see it or not.
No, they have to ask me.
Do you want to see it or not?
What is
Well,
it?
I have a half-hour video about what happened to us that didn't happen to the chimpanzees. But I'm not sure that we're ready to watch all that. Oh, you really want to watch it tonight? You got to vote on it. How many are willing to stick around for another half hour? Please put up your hands. How many are not willing to stick around for a half hour? You better just change your mind to be willing. All right, show it. Now you see, I was raised by a zoologist, and there was always this question of the missing link. What happened to the chimpanzees? I mean, what happened to us that didn't happen to the chimpanzees? Now, you know about Darwin's view. Alfred Russell Wallace thought that the good Lord made this big brain for us, and then we invented tools and language. Nobody thinks like that now. We were forced to invent tools and language, and that's what put this thing in your force. It was not the other way around like Wallace thought. But you see, we did not know in those days what happened to us that didn't happen to the chimps, but we do know it now, and this is about that. You get over here where I can see too. Sophia Krakauer, she's written a very lovely book called The Scars of Evolution, and there's lots of nice information in there that we didn't know before. And one piece of information in there is that there weren't any savannas when our ancestors came out onto the ground. There weren't any savannas in Africa at that time. The savannas came out after Lucy was bipedal. Anyway, we can discuss those things. So if you want, if you have any way to get a copy of Elaine Morgan's book called The Scars of Evolution, I recommend that to you. Now, about books, Gamow wrote 2 charming little books. One is called Mr. Tompkins in Wonderland, and one is called Mr. Tompkins Explores the Atom. Now, Mr. Tompkins is a jerk, okay? But he has an uncle who is a physicist. And when his uncle is lecturing on relativity, Mr. Tompkins is asleep in the back row, and he dreams that he's in a place where he can reach the speed of light on a bicycle. And so he's got all these relativistic effects at the speed of a bicycle. And so that's Mr. Tompkins in Wonderland. And the other one is about quantum mechanics. His uncle is lecturing on quantum mechanics, and the jerk is asleep in the back again. This time he dreams that he's in a place out in the country where this old man is making billiard balls out of first quality quantum oak. Some of them are white and some of them are red, but when they come close, the paint runs. Anyway, remember I told you that these things stay together because you don't know which one is red and which one is white. You don't know which one is the proton and which one is the neutron. Now the physicists write it always a proton and a neutron, and so they think they're really like things like that. But if it were so, it wouldn't hold together. So according to their model, they have to have gluons in there to do the jugglery there. This model doesn't do all gluons. But there's some other funny things, you see. When an electron sits on a proton, the electron has a half unit of spin, and the proton has a half unit of spin. And when they sit together, they still have a half unit of spin. So half a unit of spin went away by itself without anything spinning. That's called a neutrino. It's like the pirouette that left the stage without the dancer. In case you think these guys aren't nuts. But you see, neutrinos, like photons, don't have any existence. The emission event and the absorption event have zero separation. So the problem doesn't really arise. Well, anyway, and I should also mention one other thing. I don't have a lot of books that I wrote that you can read, but there is something of mine that got to a bookstores finally. I was at the Parliament of Religions in Chicago in this last 1993, and there were 6,500 people there. And I was an invited speaker in a special section called Cosmic Beginnings and Human Ends. Those talks have been published in a book, and that is the title, Cosmic Beginnings and Human Ends, where science and religion meet, and it's been published by Open Court, I think, in 1995. Anyway, that should be available in the bookstore. If it's not, get on their case. Now, when I was in Florida, we went to Barnes and Noble, and they didn't have it. And the man who took me there works at Barnes and Noble, and he asked them to get 6 copies. They went out so fast, in 1 or 2 days, they all went out. They had to get some more. Anyway, there's some very interesting things in there. There's something in there by a man who's talking about bacteria. I had no idea that bacteria do genetic engineering. They don't just out-survive us in the hospital. They do genetic engineering. We thought we were smart. Now, what shall I give you for homework next time? All right, there's homework to do next time. We've talked a little bit about, we haven't really talked about what happened to us that didn't happen to the chimps, but I showed you a whole movie. So now you're supposed to know all these things. What happened to us that didn't happen to the chimps. But not all of it, you see, is in there. There's some other things that happened to us that aren't in there, you see. She doesn't tell you how science arose. She doesn't tell you how religion arose, okay? That's not in there at all. So you have to think of some of those things. And if this is really a boo-boo, what the hell to do about it? If it's a boo-boo, there's something to do about it. Anyway, so we have to talk about that. All right, you guys, out of here.
Okay, now,
Ice cream.
before everybody goes,
Oh.
first of all, has everybody signed the book? Because everybody got their names in the books? Because I'd like to have everybody get together later and maybe
Have a party.
So.
By the way, after I go, you know, it would be a good idea if some of you guys get together to worry about some of this stuff, because probably it's not all salted away under your feet.
The other thing is, are we going to do it again tomorrow, or do you want us to?
Oh, yes, of course we're doing it again tomorrow.
Okay, tomorrow, same time, same place.
We're nowhere near through with this thing. Oh, and I didn't spin the rope. They made me bring this rope. Who's got my rope? All right, you can't go yet. This is not a snake. Snakes never do this. Ropes do this. Ropes do this.
Can I? Can I?
All right.
Okay, tell a joke.
This is lots easier to do on the airport floor in, what's the name of that place in Washington, D.C.? Dulles Airport. I was stuck there for 5 hours one time with the rope. Oh, it's so smooth. Okay, out of here. Oh, shut up. You follow me?
I'm getting
At the North Pole, if you swing your pendulum, it just goes back and forth, and the Earth turns around once in 24 hours.
Oh, incidentally,
Now,
this
if
is
you're
a
on
new
the
day.
equator, it's going to turn around
This
this
is
way.
August
So you swing your pendulum
18th.
this way, and the Earth turns around, it doesn't do anything.
And we're just waiting to start.
So it wouldn't be any fun to go to a planetarium on the equator. They probably don't hang those things up there.
But if you do it in Portland, doesn't it rotate in 24 hours?
No, it's not in 24 hours. Where have you been?
It's only
Or
half,
it's like-
45 degrees.
You've got to watch, see how long it takes. Stand there and watch it. You don't have to stand there a whole day. Stand there long enough for it goes quarter way around. You can multiply it by 4. It is by no means 24 hours. If it went around in 24 hours, you'd be all frozen over solid. You'd have a mile of ice over you. Any more questions you want to ask? Yeah.
You spoke about as the farther away objects are in space, the faster they're receding.
Yeah,
And as they approach, and you said as they approach the speed of light, their mass falls to zero.
yeah.
I'm not sure I grasp that.
Well, it's not as though it's such an easy thing to grasp, but that's what Einstein discovered in 1905. Einstein discovered in 1905 that matter and energy are the same thing. And we already knew that the energy goes away if something is receding, because the thing is redshifted. Of course, even we didn't know that before 1905, because Einstein found out in 1905 that the energy of the radiation is related to its color. So if it's redshifted, it's less energy. That we already knew by 1905. And Einstein, from his relativity paper, found that matter also loses its mass when it's going away. And they both go by the same number. And that's why you have E equals M. What we see as matter is just potential energy. But both the matter, the energy, is the same thing. You see, mass, inertia, energy, they're all the same thing. We've only got one of it. We've got different names for it. We call it mass, we call it inertia, we call it energy. They're all the same thing. And that approaches zero going away from you at the speed of light. It approaches infinite mass, infinite energy coming toward you at the speed of light.
You know, in a particle accelerator, doesn't a particle as it accelerates gain mass?
That's as seen by the target.
So if there
Nobody
was,
rides around behind it watching it.
so if there was an observer at the limit of the universe, he would still be at the center, would he?
Every observer is at the center of his or her observable universe.
So would he observe us as about to?
Now you see, that is the question, whether there's more than one of us. And in the entire history of physics, we have no hard evidence that there's more than one of us. We have plenty of soft evidence for the plurality of the observer, but we don't have any hard evidence for the plurality of the observer. And as Schrödinger pointed out way back in about 1940, consciousness is never experienced in the plural. See, you're just guessing that I'm conscious. You have no way to know. You have no way to know that there's anybody else here that's conscious who's perceiving this thing.
What I was wondering was if, from the point of view of the borderline,
Yeah.
would we appear to them to be about to turn to zero mass?
I think you'd have to say that. But you see, we don't know how it can happen that way. Now let me give you another problem.
Oh.
Suppose this is our universe. We'll make it smaller this time. And here we are here. Can we ask him about her?
But how can anything be outside the universe?
Well, because outside the observer, this is just a question whether there could be anything out there. So the question is, could she tell him something and then he tell us something? That's the question. So she sends the message to him and he sends the message to us. We could have gotten it direct. And we know we can't. It doesn't speed it up any to stop it here.
But because we can't get the messages, does it necessarily mean there's no messages coming through there?
No, it doesn't. But you see, as soon as you think like that, you have assumed that the universe is actual. There's no possible way that the universe could be actual. Actual would mean that it arises by a process in physics. And universes are known not to arise by processes in physics. The universe is made out of energy, and we know perfectly well in our physics that energy does not arise by a process in physics. There's some severe constraints on the notion that there's something beyond that border. There's some severe constraints. Also, you see, as we see the stuff approaching the border, it has to recycle back in. So how could it ever get across the border?
Well, the thing is, does S necessarily have to equal zero?
S has to equal 0 if one event can be seen from the other event. No, S doesn't have to be equal to 0.
So if,
Between this event and this event, there's a time separation, but no space separation. Between these two events, there's a space separation and no time separation. But if I look at you, the event which I see over there, and the event of my seeing it over here, those are 0. If a photon, look, if a photon, one of those mythical things, those mythical angels, can get from one event to another, then they have 0 separation.
but to assume
That's
that-
why I don't believe in photons at all. They fell out of the physics in 1905.
But it, you know, it feels to me that if you're assuming that S equals 0, it feels a bit ostrich-like, you know? Like how everyone's
No, this is objectively, it's objectively 0. This is not a subjective 0. This is objectively 0. Everybody in the universe seeing those two events will agree that the separation between them is 0.
Right. But suppose that there is a light source farther than we can see that hasn't arrived here yet. Suppose it's halfway here now.
Well, suppose there are ghosts dancing on the roof. You can suppose anything you like.
Yeah.
But the physicist's suppositions are constrained by the observations. That's the difference between a physicist and a jerk. His suppositions are constrained by the observational evidence.
Well, tell me, each day don't we see a little farther into space?
How? By getting up earlier?
Because the light is arriving from farther and farther each day. So is it continually expanding?
Well, first of all, the farthest away thing you see is only 2 million light years, or 2.5 million light years away, so that's not a real problem. That's not really a problem. No, I'm not sure that you could say that, because the farthest away thing you could see anyway is 15 million light years away, and that doesn't change, unless the expansion rate changes. If the expansion rate goes up, that border comes in. If the expansion rate goes down, that border recedes.
But if there is expansion, aren't you continually seeing farther?
Say again?
If the universe is expanding, if there is
No.
expansion,
When you say that the universe is expanding, you do not mean that it's getting any bigger. You mean that the distant things are going away. And the faster they're going away, the closer is the border. The border is imposed on us by the expansion rate, not by anything else. The mere fact that things going away from you go away at the speed of light puts a limit on how far you can see. You can't see anything going away at the speed of light. The funny part is they have to recycle before they ever get there anyway. So it looks as though they can't cross the border anyway. But when you say that the universe is expanding, I know the whole population of Canada thinks, the whole population of the United States thinks that expanding the universe means that the universe is getting bigger. The Big Bang people all think so. There's only a few of us jerks who see that it can't possibly mean that. But it can't possibly mean that. The border to the observable universe is imposed on us by the expansion, not by anything else. Actually, of course, we're interpreting that the redshift is due to expansion. But if you don't take it that way, it doesn't matter. The redshift imposes the boundary, not our interpretation of it. The mere fact that the energy loses that the radiation loses its energy when we look farther away, that's what imposes the boundary. Whether that's really due to going away or whether the light's getting tired, it don't make no never mind.
and that there appear to be massive quasars far out.
You can't do that with the quasars. You can't do that with the quasars because it won't work out. If you plot redshift against dimness for the big galaxies and the clusters of galaxies, redshift against dimness, they fall right across the paper almost on a line, just a little deviation from a line. And if you do the same thing for the quasars, they do not fall on that line. They fall mostly up in this corner. There's no way to interpret the redshift of the quasars as just falling on that line. They don't.
So they all are distant.
We don't know where the quasars are because we don't know what causes their redshift.
Actually, I think I'd like to tell everybody, there's maybe a few people here that haven't been here yet.
Okay, get her to sign the book.
This is John Dobson. I'm going to be passing around a book for everybody to sign, and I'm going to be passing a hat around for any donations you might want to make. He gets, well, people in other areas, okay, I got it this time. If you were to attend this lecture at a university or something, you'd pay probably over $100.
Well, you're
He
damn
wouldn't
tootin'
get
you
that.
would.
He wouldn't get that, the university would get that. But, so.
At the Academy of Sciences
whatever
in
you
San
want.
Francisco, you'd pay about $120.
But here, he's just doing it for donations, whatever you want. If you can't afford anything, that's fine. If you can afford something, that's even
But
better.
at least this money I got. I don't get any money.
Of course, it's funny money, but
That's okay. The American banks recognize it in a certain way.
yeah.
Last time I think they charged me $30 to change it.
Anyway,
This time I decided to have you do it before we cross the border.
okay, so
If you get to a border town, they can understand that there's a ratio. But if I get back to my bank in San Francisco, they charge the heck out of me to change your Canadian money. Well, anyway, you can ask all. You don't just have to let him ask all the questions. You guys can ask questions.
I have a question about the separation when it goes to zero. You
Yeah.
say that means that the light can pass
So the
between.
light beam
But
goes
now-
and get from one to the other.
But the separation equation up there doesn't say that explicitly, does it? Just
Oh, yeah.
says that the x has to equal to t.
It says that the excess is equal to t what?
For the separation to become
No.
zero,
No.
x squared has
If
to equal
x,
t
if
squared.
x is equal to t, that means the light beam can get from one to the other. If the light flash is a light year away, it came from a year ago, if we can see it now. If it came from a light year away, it came from a year ago. So you got a light year and you got a year. And they're the same distance. They're the same, and so the total separation goes to zero. But this is zero only if a light beam can get from one to the other, whether or not there are any light beams. But the reason I say that there aren't any light beams is because for a light beam the separation is zero. Now Einstein apparently asked his friend, what would a light beam look like if I traveled along beside it? Now Einstein himself thought, I don't know what his friend thought, but Einstein thought it would look like a vibration, but not like a wave. But I say, no dear, nobody sees a light beam from the side. Nobody ever saw a light beam from the side. Why? Because there's no such thing as a light beam from the side. Now you see, the equations say that our notion of the universe is somewhere flawed, because the equations do not correspond to our gut response to what we see. The difficulty is that our gut response is not what we test in the physics labs. It's the equations. And it's the equations which we know are right. And the equations say our guts are wrong. So there's this question, you see, how we got programmed like this. And now probably it's time for me to start on your case. I want to know what is the defining characteristic of a living organism. How can you tell the quick from the dead? I once saw a cartoon. These two people are sitting on either side of a card table. One of them has a smoking gun, and the other one with his gun drawn is falling over backwards. And underneath it said, the quick and the dead. I want to know what is the discriminating characteristic of the quick and the dead.
Metabolism.
Let the rest of them work at it. What do living organisms do that non-living organisms don't?
Reproduce.
Reproduce.
They consume energy.
How many of you agree that reproduction comes in here? Put up your hands if you think so. Well, it doesn't. Because if you think reproduction is it, then all the mules would have to be classified as dead. And all women past menopause. And the women will not settle with you. You can get by the mule. So that is not the defining characteristic, yes.
How about growth, the ability to grow?
Well, her answer is right. Metabolism, that is to say, living organisms have to direct a stream of negative entropy upon themselves. Do you all understand negative entropy by now? Who does not understand entropy and negative entropy? Okay. Entropy is a measure of the scrambledness of the energy. And negative entropy is a measure of the unscrambledness of the energy, the usableness of the energy. Now, gravitational energy is completely unscrambled, and the kinetic energy of large moving objects like planets going around stars, that is completely free from entropy. But all the other forms of energy are scrambled to a certain extent. Now, in this country, when you panic stop, you dump the energy of the car into your brake drums and your brake shoes, the tires and the road, and as some little kid said, it makes the earth spin a little faster that way. Second grade kid. In Europe, the milk trucks and the mail trucks run the energy into a flywheel that can be reused. Flywheel is a large moving object and it's not smitten with entropy like your brake drums and your brake shoes. You cannot get the energy out of your brake drums and your brake shoes to start your car. You can try all you like. You'll get older than I am. So, living organisms have to get a source of energy less scrambled at the start and more scrambled when they're finished with it. When you start, it's chocolate cake. And when you're finished, you flush the toilet. You must have noticed. It gets scrambled. You can't run it the other way. When my brothers and I were young, we used to, brothers are very nasty to each other. We used to say to each other, you're a hell of a guy. Everything you eat turns to shit. Well, how could you complain? But every living organism has to get hold of energy that's less scrambled than when he's finished. So the plants hold their leaves out in the sun and get the negative entropy from the sunlight. They pick up carbon dioxide with their leaves, water with their feet, with their roots. And with the help of carbon dioxide, they make a forest. Now we cut down the forest and we throw the logs in the fireplace and we burn them back to carbon dioxide and water. Where does the heat come from? It's the sunlight. It's just the sunlight. Carbon dioxide and water with the help of sunlight made into the forest. You throw it in the grate and you burn it back to carbon dioxide and water. That's what it was to start with. And it's the sunlight that heats your house, not something else. Now when we eat things, we do the same thing. The corn or the potato plants or the apple trees or whatever collected the sunlight, the negative entropy from the sunlight and made reducing agents for their own use and threw the oxygen out as waste, and we huff and puff on their oxygen and munch down their reducing agents and run around on the canned sunlight. Now let me point something out to you. Long ago, a few thousand years ago, it was not obvious probably to the people who lived on this earth that the birth of children was related in some way to something that happened in bed a few months back. Okay? It was probably not obvious. Now it's perfectly obvious to us, but it is perfectly unobvious to us that all this yakking that I am doing and all that sitting around and listening that you're doing is related to something you ate a few days ago and something you breathed a few minutes ago. We all think we're doing it. We're not doing it. You know, there's some real reason, you see, behind the monastics trying to overcome their egotism. Egotism is just a disease. We run around thinking we're doing everything, and no such thing is happening. Now, the abbot of the monastery, he used to give this example. Way up in the mountains, they harvest all these logs, and they run around this sluice way down to the lake, you see, or down to the river. And then they bundle them all up into these big rafts of logs. And then some guy with hobnail boots goes out on those logs, and at the end of the log, he puts this big stamp, okay? He says, the ego is like that. It doesn't harvest the logs. It just says, they're mine. I did it. I did it. He didn't do it at all. The other guys did it. They ran it down to the water, and he puts a stamp on it. So your ego has this feeling that it does all these things. It doesn't do any of them. See, you all have this feeling that you have something called vital energy. There's no such thing as vital energy. It's just a spook that people believe in. It has nothing to do with the real world. We eat and we breathe and we run on the canned sunlight. But it's not obvious. We feel that we're doing it. That's the disease.
What about the thinking? You're thinking with the
Well,
thought.
most of us think wrongly, so that doesn't help. But I'm trying to straighten that part out. I can't straighten out your guts. But it's possible to straighten out your thinking. That's not impossible at all. Straightening out your thinking is a possible thing.
Are you the one who's thinking, or is it the thought that thinks?
The chocolate cake I just ate probably is doing the thinking.
So it depends on what you eat it, how you think.
Yes.
Ask a diabetic whether that's true.
What?
Ask a diabetic whether that's true.
Well, what else do we need to talk about? We need to talk about the apartment house. We haven't talked about the apartment house, the atomic table. Are we ready to talk about the apartment house? Are you shaking this as no?
Yes. I shake it as no.
What?
I still have to digest.
You still have to digest this other stuff.
Yes.
Well, ask questions then. Let's get the digestion over. I should very much like it if you didn't have any problems with this stuff that we went through. But I can understand that it's not so easy to get all this stuff straight in one time through. It's not so easy. If it were so easy, nobody would have gone through my class 9 and 10 times. The record for going through this class is 10 times.
I'm working at the ego, and you said that depending on what you eat, you think,
Yeah.
and
If
who
you quit
decides?
eating or quit breathing, it'll all come to a stop.
That's right. But who decides what I'm eating?
Well, you usually have some choice in what you're going to eat. Don't you?
Yes.
Then why ask me? I'm not following your question. You decide what you eat, don't you?
Yes.
Oh,
So is it the ego who decides what you
oh,
eat?
I see what you mean. Because the ego is a product of the eating. So how can the ego be the chooser of the eating?
Yeah, that's where I'm stuck. because
Yeah,
I don't
that's where
see-
you're stuck.
Yeah.
Well, I don't know what to do about that. The choosing that you're doing now is the ego that's supported by what you chose before. You're choosing now what to eat. It's based on something you ate a few days ago. It's not based on what you're eating right now. It's like dominoes. This one fell down. That one knocked that one down. That one knocked that one down. That one knocked that one down. So what you did before is responsible for what you're doing now. And what you're doing now is choosing what to eat for what you're going to do tomorrow.
So it's neutral?
Wait a while, she's not through.
So it's neutral?
Neutral, I don't know. I haven't got a plus charge or minus charge. Well, how do I get neutral? I don't know what you mean by neutral.
It means it doesn't depend really on me now, because it always has another reason.
Now you see, me now, when you look very hard to find what me now is, it's
There is
not
no
easy.
one. Yeah, there
It's
is
very
no
hard to
one.
find what it is that you call me now. Now usually you think this is part of me, but if you cut it off, then it's not part of me. If you cut this off, that's not part of me. If you cut this off, that is. So then you say, then it's just a head. No, it not go like that. None of it is you. None of it is you, and when you die, that's what apparently you see. That none of this thing was you. Right now, we think that there's a universe outside and there's this stuff inside. That's what it looks like to us. But when you die, I'm quite sure that you see that this is part of the rest of it out there. And there's an incinerator, and this piece is going to go into the incinerator. It's all going to get burned up. And there's no way that you could have been that. It looks to me as though when people die, that's what they see. That the body is part of the perceived. If the body is in the perceived, death is in the perceived. Now you see, one thing we know from physics is that existence does not come out of non-existence. And existence does not go into non-existence. Not in the entire history of the human race have we seen anything coming out of non-existence or going into it. So if you exist, you're stuck with it. If you exist, you're stuck with it. Now the one existence that we know about is our own. The rest is a movie. The one thing that you're sure exists is yourself. Everything else is a movie. In my opinion, outsideness is fake. According to that equation, that S equals x squared root of x squared minus t squared, according to that equation, outsideness is fake.
What does it mean, fake?
Fake means it's not real.
So you mean inside is outside and the other way around?
When you say inside and outside, usually you mean that you feel that you're a body and something is inside and something is outside. If you didn't have the body, you couldn't say it. No. Now, when the body dies, it looks as though the notion of insideness and outsideness has to go. I haven't recently died, so I have this recollection, you see. And there's always this difficulty of getting this information from the people who just died. But some people have come back after just dying, and the descriptions they have sound like this. It sounds very much as though what happens is that your consciousness backs off from the consciousness that you're made out of meat. And you see that the meat is there, but you are not that. So it has a broken leg and they're working on it, or its heart has stopped and they're pumping it. Okay? All these things they do to it, but it's in it. At that time they see it as it, not as themselves. And then when it comes time to get back in, they don't want to get back in. See, I have a very good friend who had this kind of experience, and he says he did not want to get back in. Now, I don't know in what way we're compelled to get back in, but probably because they start to hard up, we're compelled to get back in. I don't know. But at any rate, he said he was not willing to get back in. And even now, you see, I've known him for several years. He's only half here. He's only half in this world, half of him somewhere else.
So you mean if there is this difference between it and this other?
And I.
No, and this, okay, this I.
There's a difference between this which is it and this which is I. Right now we think that this is I. When you die, you see that this was it.
So you mean this I is part of...
So to speak.
You mean this I is part of this one consciousness?
No, the I, oh, no, consciousness, remember we said there's only one existence.
Right.
The change is the infinite, the undivided. If it's undivided, it doesn't have any parts. Stuff that part idea. There are no parts about it. Every wave has the whole ocean underneath it. It's not a piece of the ocean. A wave isn't a piece of the ocean. A wave is the whole damn ocean.
So can you give me an idea of what it is then?
It looks as though what exists behind what we see is the changeless, the infinite, the undivided. And through a boo-boo related to the notion that we are made out of meat, we have this other notion that we see things in space and time. And in space and time, things are divided into atoms. They're made of itsy-bitsy particles, and they're changing all the time. And the change fights the change fights the dividedness, and the dividedness fights the smallness. Okay, they fight each other, the same as they do in us. We'd all like to be peaceful and quiet, but then you see we fall in love and we can't stay peaceful and quiet. We go running around mad like. Okay, they fight each other. So long as you see it in space and time, you see it as three, and they fight each other. But what exists beyond space and time, that has to be changeless, infinite, and undivided, and not three at all. The only reason we use those three names is because we're looking from inside of space and time. And looking out, we see as if it's three. But that which is infinite is undivided, is changeless. And there's only one of it. There are not two of it.
And how can you imagine this? How can you picture it to get a feeling or a vision of it?
If I were a saint, I could probably answer that.
You aren't.
No, I aren't.
What a pity.
No, I aren't. I ain't.
Pardon?
I said I ain't. Aren't is not right. When you say aren't I, it's bad English. It should be ain't I. Ain't I means am I not.
But she could say you aren't, could she?
Yeah, she can say that. Yeah.
Thanks for helping, but I don't understand what's going on.
It's an obscure grammatical point.
Okay.
Something like the ego.
It has nothing to do with that.
What is it that you're lacking to become a saint?
Me? Probably everything. Now you see, suppose you take the case of St. Francis, you see. He falls in love with God. And you can cut him up for stew meat, but you cannot get that notion out of him. You see, we fall in love with somebody, some jerk. Then after a while, we find we made a mistake, find some other jerk. It's one mistake after another, you see. But you see, St. Francis, he doesn't fall in love with the jerk. He falls in love with the ultimate reality, which is behind all this, and you can never get him out of it again. Oh, I have a piece of news that I have to give to you. I should have given it to you yesterday. I heard it on the phone yesterday. A little child fell into the gorilla haddock in the San Francisco Zoo. Fell about 18 feet, was knocked unconscious. Now the gorillas have a great big yard. There's a tree and everything in their yard and a waterfall and everything. One of the female gorillas went right over and picked up the child, cradled it in her arms, and took it over the door and waited for the zookeeper. Now you see, some of the things that happened to us at the beach happened differently to the women than they did to the men. You women are programmed to raise a family at the beach. We're programmed for hit and run. You're not programmed for hit and run. At the beach you can raise one kid a year. That's about the best you can do. But that's not true for the males. They can have 100 kids for a year. There's no problem for a man if he's hit and run. And you guys picked us out for hit and run. And we picked you guys out for raising families at the beach. But we're not programmed in the same way. And you guys think it's sinful that we run around like that. It has nothing to do with that. We're programmed to do to every attractive lady. You can ask anyone. But you guys aren't programmed that way. You're programmed to raise a family at the beach. And you guys know about human relations. We're just jerks when it comes to human relations. You all see it that way. We don't know nothing about human relations. Human relations is your thing. Language is your thing. Language almost surely started between a mother and her kid. Almost surely started between a mother and her kid. Elaine Morgan has this very interesting remark that she makes. Probably some babbling infant made an association between his babble and something which he wanted. And his mother noticed it, that he's got this babble connected with something that he knows, that he wants. And she repeats the babble. That makes it a word. As soon as she repeats the babble to the kid, we've got a word. But you see, kids, language is for kids. If the kids don't learn language by the time they're 5, it's nearly hopeless. And girls are lots better at it than boys. In a lot of ways, we're retarded compared to you guys. You can laugh if you like. This world is funnier than it looks. But women were invented by men, and men were invented by women. But as I said, I think yesterday, we did a lot better job. But you see, it's the female gorilla that went and picked up the kid, not the male. It's the female gorilla that went and picked up the kid. Now you know, you've all heard of the Good Samaritan. Haven't you all heard of the Good Samaritan? He did what any woman would have done. You never would have heard about it if it had been a woman. Don't you guys read these things? Anyway, there's some interesting things that happened to us at the beach, which we really haven't talked about yet. One of the things that we did when we were at the beach is to postpone growing up. And there's some outstanding consequences of postponing growing up. We grow up at about half the speed of a chimpanzee or a gorilla. We do it at about half the speed of a chimpanzee or a gorilla. And so when we're born, we're preemies, okay? We're all born preemies. We should have stayed in there for about 20 months to get as developed as a chimpanzee is when he is born. See, this is perfectly well known by the people who study these things. And so we're helpless compared to them. When we're born, we're nowhere near as into this world as a baby chimpanzee is. We are helpless. Now that has some very far-reaching consequences. The women have to take care of us, the mothers have to take care of us for a long time. Our brain isn't finished growing till we're 23 or 25 years old. We boys are a little more retarded than you. girls are. You finish growing your brain at about 23, we don't finish till about 25. But there's some interesting things that are related to that. And one of them is that the curiosity of childhood doesn't die away. Now a cat, well, a kit is a kitten for about a year, okay? And she tears all the buttons off your jackets and pulls your shoelaces and climbs the curtains and everything like that. For the first year, she explores everything for the first year. Then she lies by the fireplace till she's old, okay? Her kittenness goes away. And puppy dogs the same way. After about a year, they're no longer puppy dogs, they go out and mate. We don't do it that way. We're still kids, and the curiosity does not die away. And all of science and all of religion is related to the fact that we don't grow up in time. All religion is related to this wondering, what is behind all this thing? What is behind all this thing? How did I get here? What is going on here? Who runs this show?
But wild animals are always curious.
What?
You said, the analogy about the kittens and the puppies and that, those are domestic animals and they don't have to be curious because their world is limited and everything is given to them. But wild animals always exhibit curiosity.
Yes, but not like they do in the first year.
Not as much, but they
Yeah.
will always go over to investigate.
There has to be some
something.
curiosity, but not like ours. Not like ours. They wouldn't come in here worrying about why the universe is like this. They
We
don't
don't
worry
know
about
how
why
they
the
think
sky is
about it.
blue. They don't worry about why the sky is blue, or why the leaves are green, or why it's darker in the forest, or why the moon looks bigger when it's coming up.
But we don't really know what they think.
I know we don't, but we have some ideas about what they think, because we can ask them some kinds of questions.
Yeah, but we're all, no matter, even when they go to say the chimpanzee human, where they've tried to, have some kind of language between them, or there's been, work done
Well,
with
they
parrots
can't-
and
they can't do
dolphins,
language.
but we can never get across that communications barrier.
That's true, but we have some idea. We can have, if you watch a little kid and you watch a chimpanzee, you can tell something about the different ways they see things. They have a lot better musculature than we do, but we can figure things out in a way that we think they cannot figure them out. I remember a psychologist hung a clothesline across the yard and hung a cluster of bananas up there. Then he put 3 boxes in the yard, a big one, a medium-sized one, and a little one. And there's a 3-year-old girl and a chimpanzee. And he wants to know which one knows how to stack the boxes to get the bananas. The little girl puts the big one, and then the other one, and the other one. The chimpanzee doesn't do it that way, but he gets the bananas. It's the psychiatrist that got tested, not the chimpanzee. But he's got a musculature which overrides the necessity to figure it out. The girl does not have the musculature to get the bananas unless she figures it out, but she gets the bananas all the same. But anyway, there's some differences, I think, that we know between us and chimpanzees, and I'm pretty sure that there's a lot more curiosity in young animals, at least the animals that I watched when they were young and when they were older. The curiosity when they're young is outstanding compared to what they have when they're older.
Well, it's true of people also.
That's true of people also. But there's a lingering curiosity in us that lasts a lot longer than the kitten's curiosity. And now you see, one of the interesting things about us as organisms is that our brains are not finished growing till we're 23 or 25 years old. And that's one of the reasons we have these things called schools. Because if you use your brain for problem solving while it's still growing, it can get better at it than if you don't do it till it's finished growing. So the things that you use your brain for, when your brain is still growing, your brain gets good at those things, or it has a much better chance of getting good at those things than it does if you wait till you're older. It's very difficult to get language into somebody who was not exposed to it when he's young. And I think when we're 1 year old, we have something like 50 times as many connections as in our brains as we have when we get older. Some awful number like that, like 50 times as many. So they can pick up information a great deal faster. We can pick up information a great deal faster when we're 1 year old than we can when we're older. However, there's a difficulty in the language. I can't do this class for 1 year olds. They can pick up information faster, but that's not the whole problem. They're still busy with finding out what the whole universe is like in their immediate neighborhood. Which one is mother, which one is dad, which one is brother, which one is sister, which one is a toy, which one is food. They got all those problems, and they're busy working on it and finding out what's outside and what's inside. All those problems they have. Now some people who did not have sight spent their whole lives up to a certain point without sight, and then they get sight later on. There's a whole thing I read about these people, and it is very interesting. They see space out this way, they don't see space back this way. And they have no idea how far away things are. One kid threw his boot out there, and then he reached for it. He doesn't know where it is. He just reaches for it. And I remember hearing about these people who lived in the jungle. They took them out of the jungle where they could see some people way off in a field. And they wondered how they got so little.
But that's just day-to-day perceptions, because even now, and I've had this experience, you can take, like, I traveled once in Mexico, and I went to, like, by no means way back in the bush. Like, this is, like, you know, people have civilization and culture, but people were illiterate. And, you know, you take photographs so you can say, you know, this is my house, this is what it's like there. And you could show people photographs, they could not see pictures.
Oh, they can't figure out what the pictures mean?
They could not read two-dimensional surfaces.
Oh,
They
I
would
see.
take these pictures and they would be any way up, and they would be politely looking at it and handing it back to you with no comprehension whatsoever.
It's the same way with the dogs on the TV. They never watch the TV. You can try your damnedest. You can't get a dog or a cat to watch the TV.
I never really tried.
Well, I have.
I've seen cats watch TV.
That's just because they're moving. That's because they see something moving.
Well, they're usually
But
birds.
they don't make out pictures. I don't think they care about birds that they see on TV. The dogs don't see about cats on TV. They don't do anything like that.
It's only the
So
sound.
if you have a document that a cat pays attention to birds on the TV, that I'd like to know.
I'll try a test.
I don't think they do.
It's sound effects, they respond to
Yeah,
sound
I'm sure the
effects.
sound
Oh,
is
yeah.
there, but the colors were right there, too.
They'll look if it makes a sudden noise sometime.
Yeah. But that whole thing just shows that anybody probably, or just programmed, we learn to see the universe according to the experience that we've had of it.
Yeah,
That's all. It shows.
yeah. Anyway, dogs don't become couch potatoes. That's a human disease. I told my kid a few years ago, if you want to be a couch potato, study it now.
Can you imagine how it started?
How what started?
Like
Language or getting like we
the
are?
different viewpoint we have now,
I
which is
think-
obviously not really real. So it must have been another viewpoint before that.
I think see, what you have to understand is what the prime directives of the genetic programming are, okay? The genetic programming is designed to give offspring. It is not designed to give scientists or religious people. The genetic programming is designed to give offspring, and it works like gangbusters. You must have noticed. It works like gangbusters, but it's not related to knowing things or seeing things straight. It is not. It's related to directing a stream of negative entropy upon yourself and passing on the genetic line. Those are the prime directives of the genetic programming. Get something to eat and something to breathe, in our case, or in the mammals' cases. Get something to breathe and get something to eat, okay? Keep yourself well. And that's to keep the organism going. That's the prime directive, to keep the organism itself going. Then the other prime directive is pass on the genetic line. Now in our case, it's more complicated. In the case of the insects, it's under chemical control. The female insect dumps out a pheromone, and it goes off in the breeze. And the male insects pick it up with their antennae. Uh-oh, there's a female. And he goes upwind and mates with her, okay? It's under chemical control. In the dogs and the chimpanzees, it's under chemical control. The female is in heat, and the male's going to do it to her. Now, in the chimpanzees, they take turns doing it to her. Okay? They don't make love. It's nothing like that. It takes 8 seconds, and they just, you saw it in the TV. It takes 8 seconds. On the average, 8 seconds. There's nothing like making love, okay? And when the female is in heat, whole flocks of males come and do it to her. There's no way to tell whose father it is, who's the father of the kid, okay? And they probably have no notion that that has anything to do with childbearing. Now, how did I get onto that?
One thing leads to another.
What?
One thing leads to another. It's a connected universe. And nothing you do.
Anyway, the genetic programming, what I was saying about us is it's not under chemical control. See, we don't do it like the dogs. The females go in heat and all the men run after it. It doesn't work like that, okay? It doesn't go like that. So the genes have a different problem in our case. So they paint pictures, okay? A boy sees a girl, and he's got this wonderful feeling about what he sees. It's just a damn girl. But that's not what he sees. He sees all this halo of stuff around her, you see. And he thinks all these marvelous things, which may or may not be the case. Now, I had some friends in Connecticut, and that's down in the States on the east side. And when I was there a couple of years ago, she has discovered that what she married, what she thought she was marrying, she didn't actually marry. He's not really what she thought he was, and she's not what he thought he was, what he thought she was, okay? So now they're separated. They can't stand each other. They really can't stand each other, not even stand each other. And they're separated. But when they fell in love, you see, they fell in love with a picture. Each of them puts a picture of the other. It's not under chemical control. The genes have something else to do. The gonads have a picture gallery. They have a picture gallery. And that's what how we manage to do, you see. And we're programmed like this. We're not programmed to go out and have kids. That's not how we're programmed. I'll give it to the male programming. We're programmed, in the absence of females, seek females. In the presence of females, select. In the presence of a selected female, start a conversation. Ask her where she's from. Ask her where she's going. Take her out to dinner. Do I have to go on? No, you all know how it goes. I don't have to go on. But you see, we're programmed to do this from a long ways away, not by smell, not by chemical control at all. So the genes have this different programming for us than they have for the other animals. They don't have to do all these pictures for the cats and dogs. And they're not nearly so selective as we are. However, there's always a certain amount of selection. Most of the animals will not mate until they know that the other one with whom they're going to mate has proper species characteristics. Like you watch the blackbirds in mating season. They play tag. All over the place they play tag. A blackbird won't mate with a blackbird who won't play tag. That way, the flying ability of the next generation is ensured. And I was in San Francisco, and we have a pond out by at the Palace of Fine Arts where the Exploratorium is. There's a big pond out there, lake really, almost a lake. And there was this male mallard, and he's got a female mallard by the back of the neck, and he's got her under the water. And this young man, he was furious. He's going to throw stones at that bastard and get him off of her. But I had to explain to him that the male mallard cannot afford to mate with a female who can't go underwater. That would be the end of the ducks. They eat underwater. right away. It was interesting to see how fast it quieted him down.
We learned yesterday that we came from a species like animal.
We were chimpanzees.
So we were that.
I'm descended from chimpanzees on my mother's side.
So we came from there, and so we came from different genes. And what was the thing or the happening or whatsoever who changed the genes?
What happened to us was that we were forced to live at the beach for a while, for probably a few million years. Now let me tell you one thing that happens. Complexification happens. First the universe is hydrogen. Then it falls together, it gets to be helium. Then it falls together harder and gets to be carbon and oxygen. Then it falls together in a great big star and makes all the heavy elements, okay? Then the heavy elements. Then the heavy elements get together on a planet. And then we got molecules. Don't you see? It gets worse and worse. Then we get living organisms. Now every time the living organisms develop into some other state, they dump their new programming on top of the old. You always put the new programming on top of the old, and it gets complicateder and complicateder and complicateder. And we're at the end of the road. This is as bad as it's gotten so far. Well, I'll give you another example. I can show you how bad it can get. There is a bird called the malleefowl in the West, in the East Indies. A malleefowl. The female lays an egg 1/3 of her body weight. And she lays an egg once in 2 weeks. And she lays it into a compost heap, which Mr. Malleefowl has to tend. For 9 months of the year, the male malleefowl has to keep the compost heap within 1 degree. And if the temperature is warm, he lays it out in the morning and cools it off. And if the temperature is cold, he lays it out at noon and takes it up at 3. Got it? For 9 months of the year, he has to keep that temperature of the compost heap at the right temperature, because the female has a thermometer in her beak, and if it's 1 degree off, she won't lay. Now the chicks hatch out grown up, almost grown up, and they climb out through the pile and run off into the forest to escape the foxes, which sit around the bottom waiting for them to come out. Now that's the malleefowl. Now how did it get like that? Probably it got like that because sometime in the past there was plenty of compost around and the temperature was right in the compost, so the female didn't have to tend her eggs. Then probably there's some change in the weather and only the ones that tended the compost hatched their chicks. And now look how it's gotten. The male is tied up for 9 months of the year tending compost every day to keep that thing at the right temperature for 9 months of the year. And she lays eggs 1/3 of her body weight once in 2 weeks. And the kids are so grown up when they come out, they fight it off with the foxes for the woods. Now that's a complication that's thrown on top of some previous programming. The previous programming was not so complex as this. This is something on top of the previous programming. Now I'll give you another example. There was an ornithologist, and what he noticed was that when I think it was a robin, when the female robin comes with a worm for her kids, she puts it in the most open mouth. The most complaining chick gets the worm. Then she takes out a piece of dung and flies away and gets another worm. Takes out a piece of dung and flies away and gets another worm. He wanted to know what happens if I take out the dung. So he took out the dung. When she comes back, she looks around. There isn't any dung. Takes out a piece of the nest. Every time she comes, she takes out a piece of the nest till the chicks fall through the ground. Now you thought that she was properly programmed and she's a nice housekeeper. Bullshit! She is programmed if you bring something, take something. There's no other programming in there. Now, if there were a beetle that ate robin dung out of the nest, the robins that are programmed like that would fail to bear chicks. Only the retarded mothers who don't do that would succeed. And then that would be dumped on top of this programming. So long as the situation doesn't change, the ones that are adapted to the situation succeed. But when the situation changes, The ones that are over-adapted to that situation fail. Now, when we were forced to the beach, the ones that were too adapted to the forest probably failed. We're probably the misfits. But you see, on that island, there probably weren't more than a few dozen of us, and changing the genetic pattern for a few dozen is probably not such a big and impossible thing, like changing the genetic program for 120 million, okay? That would be a serious problem. But, so I think when we were marooned on that island, where there were not very many of us, and it mattered a great deal what you could do in the water. It mattered a great deal whether you had hands down here or feet. It mattered a great deal whether your hips were straight or crooked. It mattered a great deal whether you had hair on your head. What's the hair on your head for? For the kids to hang on to in the water. This is the last piece of you underwater. If it was on your fanny, they would have all drowned. It's not on your fanny, and there's a reason why it's not on your fanny. It's there for the kids to hang on to. They still do it in Tierra del Fuego. The mothers still have their kids hanging on their hair when they go swimming. Did you ever carry a kid around in a backpack? He's got you like this.
If you say
But complexity goes on piling up like this, because each time there's a change, you dump it on top of what you had before. Now it looks as though the dolphins did it in another way. It looks as though the dolphins cut off the top of their land programming and put the dolphin programming onto their immature programming. We're not sure how they did that, but it looks as though the dolphins did it that way.
By what's the criterion? How can you tell?
This is not my suggestion. It's somebody who examines the shapes of the animals and sees whether they go through a late stage in the unborn kid, or whether they skip the late development in the unborn kid. And it looks as though the dolphins skip the late development in the uterus.
And so they're born before that?
So no, it's not that they're born before that. But somewhere along the line, the last development inside has been changed to an aquatic development inside. This is not my information, and I'm a little bit helpless to give it to you straight. But I recommend to all of you that you get a hold of Elaine Morgan's The Scars of Evolution. Get your book companies to buy 100 copies of The Scars of Evolution, because there's a huge amount of very interesting information in there about how we got like we are. I am primarily concerned not just with how we got how we are, but some of the particularly interesting things to me are how curious we are and how able we are to understand the situation. And to me, that is related to neoteny, and it's related to a whole lot of things. But to me, that's the important thing. What are the characteristics of us that make us human and not chimpanzees? What is it about us that we think of ourselves as human and not chimpanzees? The chimpanzees don't have any Beethoven. You must have noticed. They don't have anything like that. It's true they can climb trees. They beat the hell out of us. And in San Francisco Zoo, I love to watch the Siamangs. And they always catch hold of a branch with an extended arm. They never do it the way we would do it, catch it like this and let the energy leak out. They never do it that way. They catch it with a fully extended arm, and they can come right down from the top and coast back up again. We won't do it. We'll catch it with a bent arm and let it out like this, and we take the energy out and we take it back up to the top. But I watch them by the hour sometimes in the San Francisco Zoo, because I particularly fond of watching the Siamangs do that. They got all these branches and things, and they got all kinds of stuff in there. So they can come all the way down from the top of the cage, almost down to the floor, and then coast back up again. Because they never do it with a bent arm. Now, the homework was is a boo-boo, yes. What to do about it?
Before we get to that,
Yes.
a little problem, you were going to talk about the apartment house. Okay.
Oh, the apartment house. Oh, yes, I have to do that.
Thank you.
I have to do that, thank you. I have to do that. I don't like to erase all this stuff. I'm going to have to erase this. Oh, Stephen Hawking in the theater. Oh, I have to tell you about Stephen Hawking in the theater. Thank you. Stephen Hawking in the theater. Stephen Hawking was talking in a theater in Berkeley, and the theater holds 3,000 people. It's a big place. And we didn't have tickets. And the program is at 8:30. And we knew if we're going to get in, we're going to get there by 7. So we got over there by 7 for an 8:30 program. And we don't have tickets. And we're hanging around in front, see if we can get anybody who has tickets. So after about an hour, we get a ticket. And then somebody gave me a sign, tickets needed. And I stood there by the front door, tickets needed. And just a little while before the thing started, we had 2 tickets and we went in. Now that was a very interesting program. There were going to be some questions. But the questions have to be given in writing. And then there's an intermission. They take him off stage and they let him read, or they read to him these questions and let him pick out the ones that he wants to answer. Now, then they bring him back on, and the moderator reads the question out, and then he has his machine fixed so that it'll answer it for him. And the interesting question was about his idea of God. That was the interesting question. What is your idea of God? And he said, my idea of God is much like Einstein's. Einstein didn't believe in a personal God. Then there was a long pause. Then he said, then his machine says, why does the universe bother to exist? You can think of God as the answer to that question. And I thought, how fabulous. He hasn't committed himself, but he hasn't backed off. Anyway, he got such an ovation for that one. Why does the universe bother to exist? You can think of God as the answer to that question. Anyway, I have to tell you about that. Now I can erase all this stuff, and that stuff, and this stuff, and the whole universe. I can erase the whole universe. See how easy that is? Now, hydrogen's like that. Now, helium, we have a +2 in here. I just write a 2. You've got to understand there's 2 pluses in there. So there's the first electron is here. Where's the second electron? Is it in the same place or someplace else?
We don't know.
Yes, we do. It's in the same place. It's in the same place. There are 2 of them in there. One spin up and one spin down. Now, in lithium, we got 3 in here. Where are the first 2 electrons? In here. Where's the third electron?
Concentric circle.
The third electron is way out here somewhere. And it won't go in there. Now, Richard Feynman was asked by a physicist, can you explain in reasonable terms why spin 1/2 particles obey Fermi-Dirac statistics? Now, Fermi-Dirac statistics say that 2 electrons cannot occupy the same energy state. Now, in this case, we have only 1 and no problem. In this case, we have 2. But one is spin up and one is spin down, and that's different energy state. Now, if this third one went in with one of these, you'd have 2 of them in the same place spin up, or 2 of them in the same place spin down. And you cannot. You simply cannot. And that's called Fermi-Dirac statistics. You cannot get them to go like that. Now, it's because of that that we have this apartment house. Now, Feynman thought that he could make a freshman lecture on that. And when he found that he could not, he apparently told the physicist, it must mean that we don't understand this. Must mean that we don't understand it. I'm not sure whether we'll get to understanding it in this class or not, but at any rate, we may get to that. but I do have to tell you how the atomic table goes. You have on the first floor, this is an apartment house, a very funny apartment house, very funny shaped apartment house, gets bigger as you go up. On the first floor, there's one room for the apartment manager and his wife. These guys. The apartment manager and his wife. You must have seen how it goes. Hydrogen, helium, and then a whole lot of them. Then 8 of them. All right. So on the first floor, there's one room. On the second floor, there's a room right over that one, upholstered in the same way. And there are 3 extra rooms. How many people can live on the second floor?
Seven.
No.
Six.
8. 2, 4, 6, 8. That's why the atomic table goes 2, 8. Now, on the third floor, there's a room over each of those rooms. And there are 5 extra rooms. How many people can live on that floor?
18.
18. So, that's 18. Now the next floor, there's a room over each of those, and there are 7 extra rooms. But you all know that the atomic table goes 2, 8, 8. The reason it stops 8 on the third row is because they start renting the next floor, where the rents are cheaper. Sorry about that. It's really 2, 8, 18, 32. It's 2, 8, 18, 32. It does not go the way it looks in Mendeleev's chart. The only reason it looks like that is because after they're filling those, they go where the rent is cheaper, or the beds are cheaper, or the energy levels are lower. But the way the atomic table is built is that way. 2, 8, 18, 32, and there's 50-something, I forget. Any questions about the atomic table?
Yes, please, can you take me through second floor again?
What?
Would you take me to the second floor again?
Second floor has a room right over the first one. And it has 3 extra rooms. 2, 4, 6, 8.
Oh, 2 per, okay.
2, 4, 6, 8.
Yeah.
Then the next one has a room over each of those, and 5 extra. Then 7 extra. Then 9 extra. Then 11 extra. We know how far it goes. Why doesn't it go there? Why don't they go there? Because there's too much electricity in the nucleus. And you cannot get it to go. Once you get to iron, you've got so much electricity inside that it fights if you put anything more in. Doesn't want any more in. So from uranium, you can get them to go down to iron. From hydrogen, you can get them to go up to iron. From uranium, you get them to go down to iron. Iron is the balance point where the energy you get out by nuclear association is just balanced by the energy you lose by electrical association. I never put it quite that way before, but that'll do. You get energy out by letting it play whole court basketball. But when you push too many plus charges together, you have to fight it. And in iron, it's balanced. By the time you get to uranium, it'll go off by itself. You just have to jiggle it in the right way, and it'll go off by itself. But iron is the stupidest stuff. Remember I told you when we were talking about stars, iron is the stupidest stuff in this universe. And once the center of the star gets to be iron, any further nuclear reactions absorb energy. They don't give it out. They absorb energy and they just collapse the bloody thing. And the whole star collapses in 3/4 of a second to the density of 100,000 battleships in a one-pint jar.
Called
Called a neutron star.
oh, neutron. Sure.
Neutron star, yeah. Yes.
I remember vaguely something from high school physics. It was about like the shells, or the, for lack of a better word, you know, where the
Yeah,
electrons
shell.
are as you go up
That's
in
it
the
all.
bigger valences. Aren't there like, the first one has 2, the next one has 7 or something?
No,
Are there
8.
some that have 7? Okay,
8.
8. So how can there be, all right, when there's 2 you have one spin up, one spin down.
Yeah.
Now what do you do when there's 8?
You have 2 in here, spin up, spin down. 2 in here, spin up, spin down. 2 in here, spin up, spin down. These are not the same energy level. They're not the same energy state. These are in the same energy state. These two are in the same energy state, except spin up and spin down. These two are in the same energy state, except spin up and spin down.
So those, the shell with 8 in it isn't.
Well, the
same
shell, they're not
energy
all in the
state?
same place.
Well, no, but nobody really knows where they are, do they?
Oh, no, we have a good idea.
In
We
there
have some
somewhere?
idea, yeah. Anyway, we do know that they're going like that. They go in by twos.
Yeah.
They always go in by twos, because two can be in the same place. With spin up, spin down. That can be the only difference between them, spin up and spin down. But once you got spin up and spin down in there, you can't put another one in unless there's something else funny. Unless there's some other reason that puts them in different energy states, either in different places or something else different.
Well, I see, so a different place in the same, like, sort of shell would be a different energy state?
Yes, there are 3 different rooms. That's why I said there are 3 different rooms. There's one room right over that one, and there are the 3 extra rooms. Now, in the next shell, which is bigger, you get 5 extra rooms. Next year, you get 7 extra rooms. Depends on how big the shell is, how much space you got to throw the rock there. It is a 3D thing, and not a 2D thing anyway. It's not really like an apartment like this. It doesn't go like that. It goes out like
No,
this.
it's more like a.
Yeah, it goes out like that.
Okay.
Now, there was something else I had to tell you. Oh, yes. Now, we talked about stars the other day. We talked about what happens in a black dwarf star, that the pressure is so high that the electrons have buzzed off the nuclei altogether, and they're just buzzing through there. Now, the curious thing is that they buzz through there in pairs. Spin up, spin down, they buzz through there. Now, by the time you have all the energy states filled for the star, you can't squash it any further. That's the other way of looking at the degenerate electron gas. 2 at a time can be in the same energy state through the star, but only 2 at a time. All the rest have to be in some other energy state. And by the time you filled up all the energy states, you have a density of 100,000 pounds in a 1-pint jar. Now, that's one way of looking at this thing. The other way is if you squeeze it down too far, you got too many electrons in too small a box, and that keeps it from going any farther. But anyway, we know that it keeps from going any farther, and it looks as though there are these 2 ways. I've heard both of these put up by the physicists. Now, on a neutron star, we squeeze them right down until they're like that. Now, what keeps a neutron star from collapsing any further? I didn't put in, because you weren't sufficiently educated, but now you are. What keeps a neutron star from collapsing any further? They're Fermi particles. You can only put 2 of them in the same place. Damn it all, you can only put 2 of them in the same place. So you've got 100,000 battleships in a 1-pint jar. All right, what happens in a black hole?
Do they pop out somewhere else?
No,
Why not?
gravity puts them in a different energy state. And they can all sit in the same place anyway. Spooky, isn't it? That's the way they put it. Gravity is so intense in that case that even if they're sitting on top of each other, they're in different energy states because of gravity. I can't figure this out nice and clearly. I'm just telling you what they say. I'll tell you some other things that they say about black holes. You've got this event horizon around here. If you cross the event horizon falling in, they say that when you cross the event horizon, what you thought was space turns out to be time. And what you thought was time turns out to be space. I have no idea what that means. I have no idea what that means. We have 3 dimensions of space and 1 dimension of time. Do you suddenly have 3 dimensions of time and 1 dimension of space? I don't know what it means. Go ahead.
What about the idea that quasars are white holes?
There
That's
is
like the opposite.
absolutely no evidence for white holes, really, I think. And the academic community has this problem with white holes. They have never been able to figure out how they could form. Nobody can do the arithmetic to get the stuff out of a black hole. Nobody can do the arithmetic to get it out. They can do the arithmetic to get it in. They can't do any arithmetic to get it out. And white holes have dropped out of the literature about 2 decades ago. Well, at least a decade ago. No, I think maybe 2 decades ago they dropped out of that literature.
Well, isn't the...
They only exist in Deep Space Nine and stuff now.
Well, wasn't the theory, part of the theory about black holes, that everything's going in and it comes out, some of it comes out in another universe,
No,
and that the
that's a white hole.
is just a reversal
That's a white hole
of
or a
that?
wormhole. That's a white hole or a wormhole, and those are in Deep Space Nine and all those things. And the trouble is they come out all reassembled.
Well,
All right, now let me tell you what it would be like. Suppose you're all in the Enterprise, we're all in the Enterprise, and we're orbiting a black hole, okay? Could we orbit a black hole all right at the distance we are from the Sun?
No.
Yes, we could. We wouldn't have any trouble with it. If you get within within 1.5 miles of it, you'd be in trouble, but not out here. We can orbit it. We can orbit it okay. So it's decided that I'm going in, okay? Who has to calculate the retro rocket? Spock has to calculate the retro rocket. If we wanted to fall into the Sun, the target is 1 million miles across. If we want to fall into a black hole, even to get inside the event horizon, the target's only 3 miles across. So let's just say we're nearly 100 million miles away, maybe even more than that, and we've got to hit a 3-mile target. Bones doesn't do that sort of stuff. Spock does that sort of stuff. All right. So I'm fixed out. So Spock calculates the retro rockets, and I'm fixed up with a big neon clock, so that you can all see it. I've got a handle on this side of it, and the neon clock is coordinated with your clocks. So I drop down toward the black hole. What do you see when you watch me? You see that as I'm going away from you faster and faster, my clock appears to slow down. Not only that, my neon on my clock gets redder and redder. The spectral lines are shifted toward the red, and you see, of course it gets smaller and smaller, so Sulu sets it on magnification 12. That's so funny. In Star Trek, magnification 12. Look at the channel is magnification 12. Anyway, in Star Trek, all these stupid words come out. Spock even at one time says 1 to the 27th power. It's still 1. You're not supposed to notice all this stuff, but we do. Anyway, so what you see is that it gets redder and redder, and the clock gets slower and slower. Now it turns out that as I approach the event horizon, as seen by you, the slowness of my clock goes almost to a stop, and with it goes my speed toward the event horizon. Ta-da. So you can never watch me cross. It doesn't matter how old you get, you never get to watch me cross the event horizon, because as I approach the speed of light going away from you, as seen by you, I seem to be coming to a stop.
But would you cross?
I don't have the trouble. I go right across. I don't have that trouble at all. I go right across. But then I have a different kind of trouble. My trouble is that my feet are closer to the black hole than my clock is, and I cannot hang on to the clock. It's pulled out of my hands. And then I can't even pull my arm down. And my shoes are long ago gone. And then my legs get pulled off on that side, and my arms and my head get pulled off on this side. And I get strung out into a long string of hamburger and crushed bone. This is just because of the tidal effects, because one end is too close and one end is too far apart, too far away. So one end gets pulled harder, one end doesn't get pulled hard enough. So it gets pulled out like this. That's not the end of it. The hamburger, because of the tidal effects on the pieces of hamburger and crushed bone, gets pulled into molecules, into a string of molecules. The molecules get pulled into atoms, and the atoms get ionized. The electrons pulled off of the protons, okay? Now, under those conditions, I can fall into the black hole. Now, in Deep Space Nine, there's some reassembly. There's some reassembly required on the other side of that stupid tunnel, which these people are not willing to face. I think that's enough for a black hole. But you do need to know that the notion is that the reason black holes can form is because the neutrons can all sit in the same place if gravity puts them in different energy states. It's not as though any place we overcome Pauli's verbot, or any place that we overcome the Heisenberg's uncertainty principle, it looks as though they go all the way through. Now let me tell you one thing, what I see. As I see it, this universe is a boo-boo, and it has to arise by pairs of opposites. We see time against two directions in space, the gravitational direction and the electrical direction. We see gravity against two directions in the electrical field, the plus direction and the minus direction. We see electricity against two directions in the magnetic field. They spin up, they spin down, okay? It's 1 against 2 against 1 against 2 against 1 against 2. Now, if this universe exists as pairs of opposites, then the total electrical charge has to be 0. It looks as though it is. Remember, I told you that if one electron in a billion billion had too much charge or too little charge by only 1 part in a billion billion, hydrogen wouldn't fall together by gravity. It looks as though the total electrical charge is 0. It looks as though the total momentum is 0. That is to say, if the total momentum is not 0, the universe is going somewhere. Well, where is it for the universe to go? You see, motion through space died in 1905. We used to think that there was such a thing as motion through space. That's what they think in Star Trek. They think the speed of light is something through space. No, there's no such thing as the speed of light through space. Speed of light always comes to you at the speed of light. Doesn't matter how fast you're going which way. Don't mean no, never mind. There's nothing to do with speed through space. Anyway, so you can't think that the universe is going somewhere. So you can think that the total angular momentum, that the total linear momentum goes to 0. Now if you think that the whole universe is spinning, then the problem is with respect to what could it be spinning. Now I understand that Stanford has an experiment to put up in space to find out if the universe is spinning. I don't know what they're going to read. But I heard that somewhere, that Stanford has an experiment to put up in outer space on one of our spaceships to find out if the whole universe is spinning. I don't know how they do that. Anyway, it looks to me as though none of those things work like that, and though the total thing goes to 0. Now it also looks to me this way, that we see a gravitational plurality by contrast to electrical duality. They're wound up against gravity by being spaced away from all the rest of the matter in the observable universe, not for some of it. They're wound up against electricity by only one pair. 1 proton, 1 electron. There's a provincial problem, skip provincial. It's a local problem. Goes to the small flames court. The other one goes to the United Nations. Gravity goes to the United Nations, and the other one goes to the small flames court. ICBC. They had to pay for my van down there. Anyway, now the question is, could the plurality disappear in the presence of the duality, and could the duality disappear in the presence of the plurality? Now, if these are a pair of opposites, as I suspect that they are, then the duality cannot disappear in the presence of the plurality, and the plurality cannot disappear in the presence of the duality. Now that's where I see Pauli's verbot and Heisenberg's uncertainty principle. There's a gravitational difference between the electron and the proton, okay? The electron is only, well, the proton is 1836.2 times heavier than the electron. Now if you have an electron and an anti-electron, they can disappear into radiation. No problem at all. If you have a proton and an antiproton, they can disappear into radiation, no problem at all. But with a proton and an electron, there's a gravitational difference between them, and the duality can't go away. In the presence of the gravitational plurality, the duality can't go away. Not in the presence of something else. In the presence of the gravitational dissimilarity between the proton and the electron, you cannot get them to merge. So that's Heisenberg's uncertainty principle. Now, in the presence of the duality, spin up, spin down, remember? Half unit of spin. Half unit of spin. A whole unit of spin we don't bother with all this. It's only Fermi particles have a half unit of spin, or 3 half units, or 5 half units, or 7 half units. Any odd number of half units means they're stuck with the duality problem. And in the presence of the duality, the plurality can't go away. That's why the neutron stars can't collapse any further. The plurality can't go away in the presence of the duality, And the duality can't go away in the presence of the plurality. That's how I see these things. And I think I could do a freshman lecture on it. Simon said he couldn't. I think I could. Now we did the apartment house. Thank you.
Thank you.
I had to do that. Anyway, now the problem is, if this is really a boo-boo, what to do about it? It's not as though a lot of people don't work at this. A lot of people do work at this. There are a lot of people who think this really is a boo-boo and that there's something to do about it, but I'll let you guess what's to do about it if it really is a boo-boo. How can we see it straight? What keeps us from seeing it straight?
Forgot?
What?
Forgot?
Yes, our genetic programming. Our genetic programming is not designed to have us see this thing straight. It is not designed for that. It's designed to give babies. The only thing that survives in the gene pool is babies. You must have noticed. Nothing else survives in the gene pool except babies. And so the genetic programming is designed to give babies. An individual can survive if he simply directs a stream of negative entropy upon him or herself. That's fine. But in order for the species to survive, they have to pass on the genetic line. So when it comes to survival of a species, or survival of any of these things what we think of as races or species, then it comes to passing on the genetic programming. How did I get onto all that? That's what keeps us from seeing it this way. Our genetic programming is not related to seeing this thing as not outside of ourselves. There's a psychoanalytic friend of mine. He's quite sure that if we saw this thing straight, we could having babies, and that's why the genetic programming has us see it this way. He's quite sure that the baby boom would immediately stop if we saw this straight. And he's quite sure that it's not going to stop.
Homo Heisenberg.
What?
Maybe there'll be a Homo Heisenberg.
And how could you come to the point to see it the other way then?
To see it the other way, you have to tell your genetic programming to go to hell. There are two things that you have to tell your genetic programming to give up. Directing a stream of negative energy upon yourself and passing on the genetic line.